All right, grade 9 science. This is the start of the electricity unit. This is video number 1, electrical forces, static electricity. So you should have notes in front of you. If you don't have those notes in front of you, you can download those on www.mrmathwell.com. Look under your Science 9 page, and you can print these out at home if you lose them or whatever. So, to fill in the blanks here, electrical forces. In 600 BC, the Greek philosopher Thales of Miletus discovered that a solid yellow material, and if you are filling in the blanks, which I gotta find my pen right here. Oh, is it frozen still? Sorry. So Thales of Miletus discovered that a solid yellow material from dead trees called amber would attract feathers if first rubbed with fur. So we have this this sort of yellowish looking rock that these feathers that are kind of flying around will actually kind of be sucked into it and stick to it. And it was noticed that if it was rubbed with fur, then this amber material would attract these feathers. So there's some kind of static attraction there.
Is amber like the hardened like sap?
Yeah, it is. Yeah. Any other questions? Amber. Okay. Similar to that. Yeah. The Greek word for amber is electron. Isn't this neat? Electron. Okay. So we have electron with a K. A lot of Greek words have Ks instead of Cs for the K sounds. Electron. Forces caused by the buildup of electrons are called electrical forces. Electrical forces. So there's a picture there for you. It's just earlier. Amber is not purely just sap from the tree, but it's something like that. Yeah. It's a solid material from decayed dead trees. So that's where the first idea of these electrical forces sort of came into play, and it's been around for a long time. This whole idea, and that's where we get our word electricity and electron from. So a force is a push or pull on an object. So this is important. There's no blanks here for you, but a force, okay, is either a push or a pull on an object. That's what a force is. Please highlight that. And in this picture here, we have, sled dogs here in a pulling a sled here. So the question is this a pushing or pulling force? Is there any pushing or pulling forces acting on any objects in this picture? What do you think about that? Look at this picture. Is something being pushed or pulled at all?
The sled is being
Hands, please. Hands. Yeah.
The dogs are pulling.
Okay, the dogs are pulling the sled. Okay, so this sled is in motion. It is in motion because it's hooked up to the dogs. The dogs are pulling the sled. Very good. Is there a push represented in this picture? A push.
If they're downhill, the dogs could be pushed.
Okay, if they're going downhill, the dogs could be pushed. Okay, I like that. Yeah, I like that thinking. No, that's right. That's good. Yep.
I don't know, but I was trying to get at with the pushing, but even when the dogs went to the ground.
All right, it's perfect. I like that. So the pushing in this is, the feet of the dogs, when they put their feet down, they are pushing away from the ground in a forward motion. So there is a push, absolutely. So this sled is being pulled, right? And the ground down here is being pushed. So there's forces acting this way on the ground, and there's also forces acting this way on the sled, right? So the sled is being pulled. I don't know if you can see that real well. Probably not real well from where you guys are. And the ground is being pushed. So in order for things to move, right, if things are moving in a certain direction, there's got to be some kind of force that's causing that to happen. So when we talk about electricity even, there is a push and pull of the forces are involved. So hard to tell in the picture, but there could be wind as well. Maybe the wind is pushing here on the back of this person. Maybe it's a side wind. Maybe it's coming sideways. Who knows? Yeah, could be a headwind, or the head is, the wind is pushing right back from where the dogs are going. So yeah, that's right. There's other forces as well. So I showed you this picture yesterday in class. The buildup of electrical charges on an object is called static electricity. This girl looks like she's having a good time. Okay, and of course she is touching a Van de Graaff generator. We had one of those in class yesterday. We had a little fun with that. And of course the buildup of charge is called static electricity.
Is lightning going at the speed of light? Is lightning going at the speed of light?
Well, the name static comes from the Greek word meaning standing or to stay. Static. And we still use that word a lot in science and math and engineering and things like that. Something that is static is stationary or standing still, more or less. Okay, static. Dynamic would be the Greek word for, or dunamos, but dynamic would be movement. Okay, it's moving. Static means it's staying the same. Static versus dynamic. All right. Static electricity passes from one object to another as sudden, quick jumps. And we call this a shock. We call this a shock. Do you guys have this picture in your notes?
No.
Oh, okay. So I'll have to adjust that. I think that's, yeah, there's a spot for it there. Something happened, it didn't copy. So you'll have to jot down a couple things, okay? So a shock here is the sudden passing of electricity. So electricity passes from one object to another as sudden, quick jumps. And this is called a shock. Static electricity works best when the weather is cool and dry. Static electricity works best. Now, when I say works best, I guess the jumping of electricity from object to object when it's cool and dry. Moisture does not allow electricity to build up on surfaces. So the more moisture we have. But moisture does not allow electricity to build up. So if it's wet and rainy and warm, then electricity is not going to be able to be built up very well. But cool and dry, there's not a lot of opportunity for this electricity that builds up to be leveled out or to be equalized. So I'll say that again, that even though water conducts electricity, that's why you get out of the lake when there's a lightning in the area. You don't want to be in the lake if the lightning strikes the lake because the electricity will travel through the water. We did a little experiment yesterday with the Van de Graaff where we built up a charge in that bottle of water that had the electrode in the top into the water and the tin foil. And we all got in a circle and held hands and closed the circuit, and that electricity passed. So electricity can be held up in water. It can be stored in water. It can travel through water really easily if given a chance to do so. But static electricity is like, when you rub your balloon on your hair, think about it, and you could maybe try this later tonight. If you have a balloon and you rub it on your hair, right after you get out of the shower, wet hair, doesn't work so well to build up, it has to be cool and dry, and then that static electricity will build up better in your hair, right? And on the balloon. So moist things. Okay, no one knows exactly what static electricity is, really, and all the reasons why charged objects behave the way they do. It's still kind of a mystery. But this little thing here, I'm not actually sure what this is, to tell you the truth. It's a bit of a it's a static equalizer, I guess, so that if you're heading to your car or you're leaving your car or whatever, if you touch this to the side of your car, it can kind of detect, looks like how much electricity is building up in the car, because the car has a lot of things in motion, has a lot of electronics, there's a lot of electrical parts, and so if your car does not have a way for the static electricity to be...
Are you planning to be in the science lab?
No, that could come down. So, yeah, if there's not a way for static electricity that might build up in your car to be released to the ground, then it could build up. You'll see in a lot of cars, especially the newer ones. I don't know, but let's say this is the back of the car here, okay, and you've got, all right, something like this, all right, and you've got the tire here, okay, all right. You'll see sometimes they have like these little things that hang down and touch the ground, Ever seen that before? I don't see them as much anymore, but they would actually drag on the ground here, and I think they're meant to dissipate the electric charge that might get built up in the vehicle.
Behind the tires, or?
Yeah, no, just underneath the underneath the back end of the car there. Yeah. So, like I say, you guys should look. I don't see them in the newer cars so much anymore. They have other ways of dissipating the static electricity, but you'll see something like that where there'd be something. Sometimes it's just one, but it's kind of underneath the car. If you look, you'll see this kind of this metal piece that comes down and rubs on the ground. So as the car drives, the static electricity that may build up in the car has a release into the ground as it drives. Yeah. Question. So yeah, if a telephone pole or something falls on your car, that's a good question, and you've heard before that you probably shouldn't try and get out or touch anything, what happens is that electricity will be trying to find a path to the ground. Okay, now that those wires that were up in the air, kind of more or less safely conducting these high levels of electricity through the wires that are suspended, not touching you or anything else on the ground. If those wires come in contact with the ground, that electricity will short circuit. It'll want to come to the ground. So if it falls in your car or something, and I've heard of this and lots of stories. I grew up on the farm. When you're hauling around large implements around the farm and you contact a overhead line, it's very serious, very dangerous. You could create this path for this immense amount of electricity to travel through the implement or through your vehicle down into the ground, and tires would burst and melt because they're trying to. Those tires, the rubber tires, would be insulators, right? They don't like to let electricity flow through them. And so as that electricity is trying to get to the ground, it forces its way through the rubber and melts it and blows it, makes holes and stuff. So yeah, so if you're caught in a car and a pole, electrical pole falls on the car and you're in there, I guess the best is to try not to get out, because as soon as you sort of try to get out and you make a contact with the ground, you might be touching the car and the ground, and the electricity can go through you and zap your fried. So you kind of want to stay still if you're still okay in there until help comes. But yeah, good question. Yep.
I don't know.
All right, so we're going to finish off the class here by watching Bill Nye the Science Guy, Static Electricity. And here's the link on YouTube. And so what I'm going to get you to do is to watch this video, and on the website, if you don't have one at home there, you can copy out this video worksheet. And this is the worksheet that I want you to fill in while you watch that video, and we will go over the answers to these questions in class.